Force, what do you have to do first? Probably need to make a free body diagram. But let's skip past that. Let's assume you have your free body diagram in front of you. Let's get to the next part. To calculate friction, what specific force do you need to have? I think I need the normal force, correct? To calculate friction, I need the normal force. So we need to calculate the normal force. Um, as I recall, that's mu times the normal force to get the frictional force. So let's do the normal force. Did you calculate the normal force yet? What did you get for the normal force?
115 newtons.
How'd you get that?
Well, because the 70 newtons is angled at 30 degrees, so you have to take the weight force minus the 70 sine 30, you'll get the normal force.
Sure. So we have normal plus whatever component of that tension is in the y direction minus 150 equals 0. Right? That's the net force in the y direction. And we need the component of the tension that's in the y direction. That's probably 150. I'm sorry, that's probably 70 times the sine of 30, which is 35. So normal plus 35 equals 150. So yes, normal is 115 newtons. Come on, folks. This is like, physics honor stuff. And yes, I expect you guys to do that. But that's not the frictional force. 0.3 times this gives you the frictional force, correct? So 34.5. All right, now that you know that, I want to talk to you about something. We're going to compute what's called net work. And there's two different ways to calculate net work. The first is what we're going to do as an example, which is to compute the work from all the individual forces. And then just sum them. The next way is to compute the net force. Then calculate work. That's two ways to calculate the net work. So again, one of them is to calculate the work from each individual force, and one of them is to calculate the work from the net force. So I want to teach you both ways, but I'm only going to show you one of them. And then we're going to learn there might be other ways to calculate net work as well. Let's assume that this force is used to move the box 3 meters. How many forces act on the box while it is moving the 3 meters? That's a pretty easy question, folks. None of you? How many forces are acting on the box? I think 4. Let's name them. Wow, this is a rough crowd. Name one of the forces acting on the box. Gravity. Good job. Way to go. Way to hit that low-hanging fruit. Name another force acting on the box. There's a normal force. We just talked about it and calculated it. What's another force acting on the box? Friction. Good job. We're doing great. That's 3. What's another force acting on the box? Tension. 4 forces acting on the box. Right. So we're going to calculate the work from each one of these forces. Now, last week we talked about calculating the work. If you don't remember that, work is equal to force times displacement times the cosine of the angle between the force and the displacement. So if the box is going to slide across the floor, let's calculate the work done by gravity. What is the force of gravity acting on the box? 150 newtons. And how far does the box go? It goes 3 meters. And what is the angle between gravity and the displacement? 90. So how much work is done by gravity? Absolutely 0. Why? Because the work and the force and the displacement are at 90 degrees to each other. Let's move on to the next one. How much work is done by the normal force? All right, there's a normal force. You just calculated the normal force. What is it? 115. But the important thing is, what's the angle between the normal force and displacement? 90 degrees. Is the normal force doing any work here? No. So even though we might know what that force is, because we did spend a few minutes talking about it, it does no work because there's no component in the direction of motion. Only two forces actually do work here. The tension force does work, and the frictional force does work, because those two forces have components in the direction of motion. So, friction. What's the size of the frictional force? 34.5 newtons. That's right. And how far does the box slide? 3 meters. But what is the angle between friction and the displacement? 180 degrees. That's right. Making the work done by friction negative. How much work is done by friction? Yeah, this part requires the old calculator. A little multiplication there. So I can rely on anybody to do this one. Work changes an object's energy. This is negative. This is taking energy away from the box. All right. Next, the tension does work on the box. What's the size of the tension force? And of course, the box still travels 3 meters, but what is the angle between the tension and the displacement? This is our 30 degrees. Heck yeah, there we go. So, not too tough. Handing you the easy stuff first. It's not going to stay this way. So this method is this bottom one. This top one right here. We're computing the work from the individual forces. That's what we are doing when we sit here and calculate the individual amount of work. So add those things up. That's the total work done on the box. Not hard. It's going to get harder. Again, throwing you the easy stuff first. I got about 78.4 joules of total work done on the box. This is the net work. The issue is, though, whoever pulled on the box lost 182 joules of energy, right? They had to give that box 182 joules of energy. But then the floor took away 103.5 joules of energy, leaving the box with 78.4 joules of energy. Now, at the same time, you could have computed what the net force on the box was. You got 30 seconds to tell me what the acceleration was on the box. A Unit 2 problem, and I'm going to pick one of you guys to give me my answer. Yeah, sounds about right. Happy to hear it. So the acceleration, 1.74 meters per second squared. The mass of the box was 15 kilograms. So the net force is going to be 15 times 1.74. Now there's a couple different ways you could have gotten this 1.74, by the way. You didn't have to do a net force problem. Benson, did you do the net force problem to get that, or did you do it a different way? You did do net force. Okay. I'm going to show you that there was another way you could have done it. But let's use your net force. If we take that and multiply by 15, your 1.74, and multiply by 15, we get that there was a net force of 26.1 newtons acting on the box. All right, all I did was take the mass of the box and multiply by the acceleration. That's the net force acting on the box. You probably had this a minute ago before you divided out by the mass, right? But if I asked for the net force, I'm not sure I would have gotten this, even though that's what you did when you added up the two forces in the x direction. Now, the box moved 3 meters, so the net work from that net force is going to be 26.1 times 3 times the cosine of 0 degrees, because the net force is in the direction of the acceleration. So that's going to be a cosine of 0 degrees. And lo and behold, what do we get? 78.3 joules. Accounting for a little bit of rounding here, I think we're right in the same ballpark. But you know what you could have done, guys? You could have, and I'm showing you an alternative because there's a lot of ways to do these problems. You could have set this equal to force times displacement. Right? You could have done it from the beginning. You knew the box was moved 3 meters, so you could have found the net force from the net work. And that would have worked out just fine. There's a lot of ways to do these problems. Consider looking at the alternatives. So take a moment. All right, then we're going to do something as an aside. And I want you to pay very close attention to this because I want you to see something. We defined net work 2 different ways. One of those ways was finding the net force and using the net force to compute work, which means taking net force times displacement and assuming that that the net force was in the direction of the acceleration, which is a reasonable assumption. It also is assuming that your object is traveling in the direction of motion. But what we're saying is this work is going to be used to change the object's velocity. That's what we're hoping, because it's an unbalanced force causing an acceleration. If I do just a little bit of substitution, a reminder that net force equals ma, I can substitute here ma for net force. And we're going to have cosine of 0, which suggests then that we can have a cosine that equals 1. Now, do you remember a while ago what this equals? V squared minus V naught squared. That's right. Right, from way back in the day, a little bit of kinematics. All right. If I divide this by 2, I'll get 1/2 V squared minus 1/2 V naught squared. Can you see why I'm doing this? Can you see why I'm doing it now? It's always easier to measure velocities and accelerations, isn't it? I'm going to do a substitution then. So I've taken this, subbed it in for a delta x, giving me 1/2 mv squared minus 1/2 mv naught squared. I know some of you know what this is. Tell me what it is. This is kinetic energy. We define kinetic energy as 1/2 mv squared. A couple of points here that are important. Kinetic energy is the most basic form of energy there is. It is the energy of motion. So when you were doing chemistry and telling me that the motion of the particles defines the temperature and as the average kinetic energy of the particles, this is what we meant. This is how you can compute the velocity of particles in the sun that are causing fusion. You can do so by knowing the temperature, because it not only gives you kinetic energy, but it gives you their speed. But I'll point out it doesn't give you their direction. You'll notice that the velocity is squared. Whenever you square the velocity, you take away any of the directional information. That's because energy is a scalar quantity. Scalar quantities don't have direction. It is just an amount. But also, it should be very clear, kinetic energy can never be negative, right? Because none of the components that compute it are negative. However, a change in kinetic energy could be negative. But obviously, an object's change in kinetic energy always requires a change in speed. That's an important distinction here. And I bring that up because there are situations in which an object's direction changes, but their kinetic energy doesn't. We just did a whole bunch of them, if you'll recall. I mean, think of this one for just a minute. This is an example come on, just stay over there. This is an example we did just last week. Although, judging by your test, not everybody knows this. And I don't mean that to humble you. I mean that because I'm still reeling from some of your test scores. Some of you did great, though. I got to be honest. There was a lot of really good test scores and all there, too. But boy, AP1's test scores are bad. Got to grade that sucker today. Moon going around the Earth. There's a force acting on the moon. What's the direction of the force acting on the moon? Towards the Earth. That's right. And that would be the force of gravity. Good job. What direction is the moon going? We had a name for it. How would I describe the velocity of the moon? Tangential would be the word I would use to describe the velocity of the moon. And the tangential velocity of the moon is this way. Force of gravity is towards the center. Velocity of the moon is tangential. What is the angle between radial and tangential? 90 degrees. So the force of gravity is causing the moon to change direction all the time, but it can't change the moon's speed, which means although there's an unbalanced force acting on the moon, there's no work done on the moon because that force isn't causing a change in kinetic energy. So this is an example that shows that not every time having an unbalanced force results in work being done. If the unbalanced force only changes direction, then it doesn't change the object's kinetic energy. Remember, the definition of work said there has to be a component of the force in the direction of motion. If there's not, no work is being done. And since you guys are easily led and sometimes fooled, think about how I could do that to you on a, say, multiple choice test. That's what they're going to ask, this question specifically. So an object in centripetal motion is accelerating, it's experiencing an unbalanced force. Is work being done? And the answer will be no. And that will be true in any situation in which an object is in centripetal motion. So be very careful. Centripetal forces or forces causing centripetal accelerations do not do work because they do not have a component in the direction of motion. But now that we know this, that the network equals the change in kinetic energy, you have a third way of calculating net work. You can calculate net work by calculating the individual amount of work from every force. You can calculate net work by getting the net force and then multiplying by the displacement, or you can calculate net work by computing the change in kinetic energy. 3 ways of computing net work. So, show me. If I have a cart that's traveling, say, 3 meters per second, so there's my cart. It's traveling 3 meters per second this direction. And over the span of 2 meters, it's now traveling 4 meters per second. If the cart has a mass of 1.5 kilograms, how much work was done on the cart? In fact, I have 3 questions. How much work was done? What was the net force on the cart? And how long did it take? Let's see what we got. So where's number 16? That's twice today, but you didn't give us the answer last time, so you can give me any one of these answers. Do you have? Force is what? How'd you get that?
I put it equal to MA, so 1.5 is M and acceleration is 3.
How'd you get the acceleration?
Oh, that's 3 meters per second.
Yeah, that's a velocity. Now, you could get the acceleration. There's a method to get the acceleration. It's not quite the order of events I wanted you to do, though. So I'm not going to let you go on this one, okay? Here's what I expected you to do. I expected you in this problem to recognize I gave you the initial velocity and the final velocity, which suggests that you could probably calculate the change in kinetic energy as your means of getting the net work. This is what I expected you to do. Now, you didn't have to. You could have gone about it the way you started to describe, which is to get the acceleration and then find the net force. That is another way to do it, but I would have preferred you do it this way. Which is, here we go, 1/2. What's the mass? 1.5. What's that final velocity? Squared minus 1/2 times what's that initial velocity? I'm sorry, what's that mass again? What's that initial velocity? That's what I was looking for. When you work all that out, what do you get? 5.25. That's right. And the unit there, joules. Remember our units here, joules. Excellent. Now, person number 5, how would you get the How'd you get the net force from that?
I don't think he's.
So one of you two, since you're on either side of 5.
Which one?
Let's go with net force. It's next.
We did 5.25 equals force times displacement, and we just divided 5.25 by 2 meters, and we got 2.625 newtons.
That's it. That's all you had to do. So net force times displacement equals net work. So divide 5.25 by 2. And what's that number again?
2.65 newtons.
Excellent. And I have to roll one more time. 24. Where's 24? 24. Can you tell me how long this takes? All right, Chase. I'm not going to let you out of it, though. This is a Unit 1 kind of problem. And I'll remind you, time never showed up all that much when we did force problems. Do you guys remember that? Forces could tell you the size of an individual force, could tell you an acceleration, but time showed up quite a bit with Unit 1. It showed up all the time, as I recall. The only time we had time was recently when we did orbits, but that's not has nothing to do with this. So I think we're looking at a motion problem. And we have initial velocity, we have final velocity, we have displacement, and we're looking for time. So let's break out one of your motion equations. Do you remember those 5 motion equations? Do you have them written down someplace, Chase? So is it not accessible right now? Well, that's going to make it difficult, and we have other teaching to do today. So this is probably what I would have used. It'd be the most direct way to figure out how long this took. We're going to have to do a little better. So there's not a whole lot here, but it was a first semester topic, or I'm sorry, first unit topic. So who's got the time for me? Go ahead. 0.57 seconds. All right. Now, I wanted the time because there's something here that I think we need to add to this. First, work is how you change something's energy. One of the most basic ways of seeing that the energy was changed is by seeing a change in the speed of the object. So a change in speed means a change in kinetic energy. Now, I do want to be very clear. Net work equals the change in kinetic energy. It doesn't tell you how much kinetic energy the object has. It tells you how much the kinetic energy changed. So it doesn't necessarily tell you how fast something's going. It tells you how much their kinetic energy changed. So that could tell you how much their velocity changed, but it may not because it's v squared, not v. However, there is this other thing that we're going to have to also introduce, and that has to do with how fast we do work. And it's called power, and power is the rate at which work is done. Most simply, it's work over time, but we're going to come to define it a couple of different ways. But it's the rate at which work is done. It's how fast work is done. So generally, all cars can get up to 70 miles an hour. But some cars can get there faster. You're paying for how fast the work can be done. Getting the car to that speed isn't a big deal, but if you don't want to take all day to do so, you pay for an engine that can get you there faster. So power is the rate at which work is done. In this case, we did 5.25 joules of work, and we did so in 0.57 seconds. Work over time. It's one of the simpler ways to calculate power. Now, as you guys are running off to calculate this, there's something that you should understand, and that is there's a unit associated with this too. It is a joule per second, which is also known as a watt. A watt represents how fast work is done, or how fast energy is consumed. So when we measure things in watts, we're talking about the rate at which you're using energy. So a change in energy divided by time is going to be another way to calculate power. Now, for this particular thing, I want you to remember a joule is a kilogram meter squared per second squared, and now we're dividing by seconds. So the base unit is kilograms meter squared seconds cubed. Power. All right.